have Nikita Zhivotovskiy.
Yes,
right?
perfect.
New professor in Berkeley stats, talking about learning thresholds. So one of my favorite topics. Thanks.
Yeah, thanks so much, Adam. Thanks for the invitation. So we're slightly on schedule. Oh, we're still on schedule. So I'll start with the. Yeah, perfect. So this is a joint work with Jan. He's here, and with Sasha Rachlin. He's in Spain, not at MIT right now. So we have a recent paper. It's called differently. So the idea here, I will just try to rephrase the same results we had in our paper in a different order. So the picture will be somewhat slightly different. So here's the example all of you know. We observe a sequence of points like x1, xt that belong to the interval 0, 1 interval. And they're labeled by some threshold. And this threshold puts either +1 or -1 label on each point. And here how we have it in the online or sequential setup, right? Imagine that the adversary gives you the point 1/2, and they ask you about the label of 1/2. So you're saying 1, they're saying, no, you were wrong. And they send you to one branch of the tree. Then they ask you about 1/4, and then you're wrong again. So in some sense, they can, or in the other case, if you're correct, or if you say -1, then they will send you another branch, and so on. So you have this so-called little stone tree, and the adversary will force you to make infinite number of mistakes, like you'll do them forever because of the structure of this interval, but the adversary will always be consistent with one of the thresholds. So the adversary will always, so there will be a separating threshold that is consistent with the point we've seen so far. So thresholds is a particular example of classification with half spaces. So it's a linear classification. And the question we're asking is the following. How does the difficulty for online learning thresholds affect learning with other unbounded losses? Like, for example, the logistic regression loss, it's minus log of the sigmoid like this. Hinge loss, so something we know very well, or the regression with square loss. It's y minus x theta squared. Right? How does it affect? So let's consider the sequential linear regression setup first as a particular case where we don't have a binary loss, but something more subtle. And of course, I'm already in the real valued case, vector case. So xt's design vectors now belong to the set Rd. The response variables are real valued. So at round t, again, sequentially, I have access to this data, x1, etc., xt minus 1, yt minus 1. And my aim is to predict the response variable yt at round t. Right? So what algorithm should I use? So this is a classical predictor. Many of you are familiar with it. It's called the Wolf-Kazur-Wormuth predictor. And it works as follows. It takes at round t, it uses the weights that are minimizing our classical reach, right? So this is a loss up to the moment t minus 1, plus the reach penalty. But there is one little twist, right? In some sense, I'm adding the current point xt with the 0 label, right? So I'm kind of, in some sense, I'm transductive. When predicting the new point, I use the information about this new point instead of pre-training everything based on the data set up to the moment t minus 1. So this is a little twist. And this little twist allows to obtain this famous result by Vovk. Now, of course, I think people mostly know Vladimir Vovk as a creator or pioneer of conformal prediction, but there are many, many online learning related results from 90s by Vladimir Vovk that are, we're mentioning here. So here is the regret bound, right? Assume that my xt's, right, are bounded by some constant r. The norms of xt's are bounded by some r, and assume that the response variables yt's are bounded by some m. Then the following regret bound holds. The total loss in the sequence of length t of my predictor is less or equal than the total loss of any fixed rule theta star. And then I have the term which corresponds to the norm, the Euclidean norm of the solution, and the term that corresponds to the dimension of the space, m squared, which is the bound on yt's, and some logarithmic factors that in particular include the radius, the dependence on the norm of axis. So if you think of if you compare with the thresholds, we're in a much better shape, right? Because for thresholds, we had infinite number of mistakes. Like no matter what, this is unlearnable. And when you see Wolf's result for essentially the same linear structure, but for the squared loss, suddenly you see that there is no Littlestone dimension, no infinite depth. So you just pay the dimension, but t can be very large, and the dependence on t is only logarithmic. The only problem here, or the only little subtlety here, is that the bound still has some dependencies, right? It has dependence on the norm of the optimal solution, and there is a dependence on the norms of vectors xt. So in some sense, it's not completely like, there is still something, or you can find some regimes where the regret bound will be linear in t when either this is too large or when the norm of theta star is too large. And we'll see soon that essentially the Littlestone example, this kind of depth of the threshold, is reflected for other losses exactly in this additional dependence in some parameters, right? In some sense, this threshold is reflected in something not very obvious, right? Like in some of these extra terms, most importantly, this essentially unavoidable dependence on the norm. And this will work for all reasonable losses, for logarithmic loss, for hinge loss. We'll see in a second. Now, in order to have some maybe playground, we need to return back to thresholds, to the binary classification, and we need to ask this following question: how do people in the literature avoid this difficulty of thresholds, right? How do you avoid this infinite tree, the branching tree that where you make an infinite number of mistakes? So one of the tricks will be to assume that the data is IID, and then people do these regret bounds for kind of essentially non-adversarial data. Another example we're all familiar with is the margin assumption coming in the analysis of the perception algorithm, right? The classical Novikov's analysis was essentially in the linear case, right? It was a linear classification, but there was margin. So margin is another alternative that doesn't allow this infinite branching. Another thing which Nikita is unfortunately not here, but this is also a hot topic, is a smooth online learning when we believe that the data is generated from some kind of stochastic mechanism, and there is certain density of this mechanism that changes in time, but not too much. There is we control the ratio with respect to some base measure. So, but since this is not studied at all, we'll focus on the maybe arguably the simplest possible online setup that bypasses this problem of thresholds, is that the set of x's, the covariates, are known in advance. Not their order, but only the set. So somebody gave me x1, xt in some random order, and I want to exploit it. Now, why does it allow me to bypass the problem of this branching tree, like infinite number of mistakes that I showed you before? Because now it's very trivial. So you give the set, you take a look at the set x1, xt. Then, of course, you know that threshold, there are not so many ways how thresholds can split this into two classes. You can just order them the real line. And then, of course, just by halving, just by majority vote, essentially, you will make only the logarithmic number of mistakes on any sequence. So you don't need to kind of, again, or the adversary doesn't have the power to put you in these different branches and always to force you being wrong. So the motivation between this simple setup, or two motivations. The first one is like, it's a simple playground which allows you to bypass the difficulty of learning the threshold. So it's like the simplest extra information you might get, like the simplest piece of information that you might get, so that this example doesn't exist. Another thing which is more important from the maybe practical perspective, it appears it's not hard to prove that these transductive online regret bounds, everything you proved essentially in terms of regret with knowing x's can be immediately converted into a statistical excess risk bound. So the classical online to batch argument tells you prove something sequentially and jump into the batch world. Here I'm saying no, you can use even more. You can use the information that actually you are going, or you are planning to online to batch convert it. So then you can essentially assume that you know the axis, and then you can convert these sort of algorithms into the batch algorithms. And if you get improved regret bounds when knowing xds, then of course you will have improved excess risk bounds. So we'll see examples soon. Right, two things. there are any questions, yeah, please raise your hands, because I'm going pretty quickly. I'm sure many of you have seen things like that before. Okay, the question is, can we improve Wolf's bound when we know access, when we know the covariates in advance? And some great people, so Peter is giving a talk tomorrow, right? Manfred Wormuth is very famous in Cold Community, and some of their brilliant co-authors, they actually started studying this in, like, I think it's called 2015, like around 9 years ago. And the result, or the best known result in the context of linear regression, when X is unknown, was given by these people, Gayar, Gershinovitz, Huar, and Stolz. And this is what this is their result. Again, it's a very simple modification of Wolf's online linear regression algorithm. You, at round T, you use the same squared law, like the same Rich style predictor with the same term, but the Rich penalty is changed, right? Before, in the vanilla setup, it was like a Rich penalty where you pay the Euclidean norm of theta vector squared. Now you use your covariates and you introduce this term that uses the entire sequence of x's in the penalty. So you see the summation here is from up to t, so I know all the x's, while of course for y's, I only know them up to the round t minus 1. So this is it. And the result, actually it's surprisingly simple. I think most of you already have a guess on how you can convert Wolf's result for ridge regression into this result. You essentially rotate using like the sample covariance. If you know x's, you can just essentially do the PCA style analysis, and then with some algebra, you can convert the proof or the result of Wolf into this bound. Now, what is interesting about this bound? That the sum of my losses is less or equal than the like opt. And then there are two terms. Yes, there is dimension. There is magnitude of y's, but that's it. So norm disappeared. So there is no theta star. And there are no assumptions on x's. So all the radius of x's also disappeared. So the only thing I have on the right-hand side are these kind of three parameters. And of course, neither dimension can be removed, nor m can be removed, the magnitude of y's, just because the problem scales with m, right? It's proportional to, the regret is proportional to m squared. So it looks already much better than it was before. And if you take a look at the simplest implication, you just choose the optimal lambda, which is dimension over t, then you have a very neat regret bound that depends for the unbounded loss. So this is an unbounded loss, right? Because x's can be large, theta star can also be large, right? That depends only on dimension, magnitude of y's, and number of rounds. Of course, when I'm saying that there is no dependence on the norm of x's, you feel that it's not a big deal because we know x's, right? We can, without loss of generality, assume that they're less or equal than 1. So this assumption is for free. But still, there is this theta star, right? The theta star that you technically have to pay in the standard sequential setup. Now it disappears, right? Like there is nothing like that. And the question, again, it's more kind of returning to the next question or just continuing the same story. In this setup, for which loss functions can we obtain this d log t type regret, this nice regret bound, that is independent of both x's, like or norms of x's or magnitudes of x's, and the norm of the optimal solution, right? So I just want to understand, is it like something specific to the squared loss, or we can continue on? And next examples will be even, I would say, more relevant. So the next example, maybe before giving the example, I will run into, yes.
There's this old result of Moss and Turan about online learning of half spaces just with respect to the 0-1 loss. There, you know if it's in d dimensions and you know the size of the, like each xi is from a discrete set of size n. Then you get something like d log n.
Yeah. For binary loss,
that seems less a weaker assumption than having to know that x1 through xt in advance.
Yeah. So here the x1, xt knowing in advance, of course, again, as I mentioned, it's a kind of a playground, which is the simplest extra information that I get to bypass it. And also knowing access is, again, for free for batch. So if you think of always converting your sequential results into batch results, then again, it's for free. I think kind of extensions where you kind of assume less are very interesting. Right? So for example, smooth online learning results of this form, I think they're kind of open, right? That's we don't have it. Okay, so this is the thing. And how do we analyze it, or what is the approach? So the analysis of Wolfka is, again, it's something very classical now. It's on many textbooks. And if you open any of the recent surveys, usually people just use the analysis of TRL and some linear algebra to prove the regret bound. The same you can do with this no one axis. It's just analysis of follow the regularized leader, some linear algebraic manipulations, and you get the bound. But Wolfka's original approach was different. So he was thinking of this entire linear algebraic arguments as the instance of exponential weights. So he was doing continuous exponential weights, choosing some smart priors, computing posteriors, using it was a very nice theory where he created this regret bound as an output of multiple logical steps and computation of certain Gaussian integrals. Let me remind you what exponential weights or multiplicative weights is. So I have some losses parameterized by some parameter theta. So for example, theta is a subset of RD. And then I have some prior distribution. For simplicity, it will have some density, mu over the set theta. And then for, at round t, my distribution rho t is as follows. It's proportional to the prior times exponent of the total loss up to the of theta, right, up to the moment t minus 1, what I've seen so far. So I can construct this distribution, this measure over the set of parameters at step t using the previous t minus 1 observations, right? So again, why I'm saying that we're going beyond FTRL and linear algebra, because we can use the cases where the linear algebraic analysis of Wolfka doesn't work. So for example, let's again try to understand what's happening when I want to get some sparsity.
So what happens in terms of the computational complexity? So Bob's thing is, it's a convex minimization problem.
Yes.
Now here, even for nice priors mu, can I sample? I mean, maybe for nice priors mu, I can sample from this, but for general ones, maybe not.
So I think it's a great question. Thanks. So the idea is the following. So if, for example, for the squared loss with squared prior, it will be essentially sampling from the Gaussian measure. Yeah, and then because we're sampling from the Gaussian measure, the final predictor, you will see the form in a second. It will actually build some Gaussian integral, which converts to ridge regression in a particular case, or ridge style regression in the particular case of linear regression. Now, if you are lucky enough with, for example, some sort of a hinge loss here, right, then it will be convex, then Gaussian. So you have a certain log concave measure. So a lot of people study this log concave samplement. There are many papers around this.
As long as the prior mu is good too. Right?
Yeah, so you have a combination of good loss, good prior, and hope that sampling results for log concave measure are practical enough. Yeah, of course, it's not necessarily true that this will be, efficient, or even if it's polytime, sometimes the computational, very high powers in dimension and in the sample size. Right. So in some sense, exponential weights is not, I would say, the best from the computational perspective algorithm, unless you have some tricks or some special cases.
So let me just ask another follow-up, but feel free to ignore it. So in the case where you have the square loss, right? Okay, so you get those Gaussian that you're sampling from, but presumably the posterior mean has a closed form. But maybe for things like the hinge loss, it doesn't have a closed form. I mean, so somehow the linear algebraic things that you're avoiding, can one think about it as an instantiation of this viewpoint in cases where it is a closed form, but there are other cases where there is no?
Exactly. So this is the whole magic. So there is a special case where linear algebra is equivalent to this computation, and this is where you can rotate and use PCA style things. But I'm jumping somewhat out of linear algebra. You cannot do it with, or we don't know how to do it with FTRL, but we know how to do it with this magic. Computational questions aside, or with some, paying more for computations. Yeah, okay. It's good that you jumped exactly into this question. It simplified my my presentation actually. So for example, again, it's more like an example of how can you take sparsity into account, right? I'm not into this maybe lasso theory now. I just like try understand what we get if xt's are known. There is some magic of choosing the right prior. And of course, people did a lot of exponential weights analysis over the last maybe 15 years with certain priors that favor sparsity. Here's one of the priors. So assume that in R, I take the distribution or density that is like this. It's relatively heavy-tailed. And then I put the following prior. Again, it's a scary formula, but it's based on the product of d priors of this form normalized by the coordinates of x's. So kind of, because I know x's, I can construct a certain prior, which is the product of d densities of this form modulo this normalization constants, right? And some scary heavy-tailed prior. And it's not very hard to sample from it, right? Because we know how to sample from individual densities like this, and it's just a product measure. And yeah, I'll just present the result we have in this direction, so that if I define this quadratic form, so this is a total loss up to the moment t minus 1 and a loss of an extra fixed point x and y, then there is this integral based predictor. It's related to Ankur's question of how the predictors look like. It's some Gaussian integrals, not necessarily super computationally nice, but still it's some kind of an expectation. You may think of it as expectation of this random variable with respect to the particular Gaussian measure that you observed up to the point t minus 1. But maybe then not the form of the estimator is the most interesting, but the form of the regret bound. That assuming that y's are bounded by some constant m, I can provide the regret bound that depends on the sparsity parameter s, the magnitude of y's m squared, and it doesn't depend again on the norm of theta star. If you take any lasso or bound, like the random design or fixed design, usually there will be some price for the theta star in the bound. Here there is nothing. And also this compatibility RIP star type constants, if you open this literature from 10, 15 years ago, usually they're polynomial somewhere in the bound. Again, because there is some exponential weights magic happening, for some reason, this is logarithmic or you put it under the logarithm. So you have a much better dependence on the compatibility constants. And again, you don't pay neither for the theta star nor for the norms of x's, only for the ratios of x's that are hidden in this compatibility constant. And of course, you cannot prove this by linear algebra, right? This is already exponential weight style result. Right. Okay. So the next result, which might be even more interesting, more relevant to what people do right now, nowadays, we're slightly out of sparsity recently. So this is logistic regression with the logarithmic loss. So I want to classify x as either minus 1, 1. So this is a standard sigmoid. And I use the cross entropy or logarithmic loss. It's minus log of the sigmoid. Now, if I want to start with the regret bound, I will put everything in the ball of radius b, Euclidean, the set of parameters to the Euclidean ball of radius b. And again, without loss of generality, I will put for simplicity all x's in the unit ball. And the question is, the classical information theoretic or probability assignment question is, what is the difference of the total logarithmic loss of my probability assignments of points with labels minus the essentially these like up to the sign or minus, it's like a likelihood. Like this is the minus minimizer of the likelihood. No, maximizer of the likelihood. Right, this is the classical regret bound for the logarithmic loss. People studied it a lot in the classical setup without known x's. If you do the online gradient descent, you see you pay theta star. This is how the analysis goes. We're claiming, as you recall, that theta star is something specific to not knowing x's or something specific to this Littlestone tree. So this is we're returning to the same concept again and again. So if you do the online Newton step, then you can prove this. Maybe bad dependence on theta star. You remove the square root t, but you still pay theta star. Now, the state of the art in this direction was appeared in several papers. This is exactly the exponential weights. And in exponential weights, you finally have a logarithmic dependence on the norm of theta star, but it's still there, right? It's under the logarithm, but you paid. And there are multiple papers. Again, the analysis is somewhat related to the original analysis of Wolf on running exponential weights in a continuous manner over this. In that case, it was a squared. For Wolf's case, it was a squared loss. And in this case, this is all about the logarithmic loss. And the interesting aspect, in one, I started with this little stone tree, and I want to return it to it again, is that there is a matching lower bound that shows you that you need to pay the norm of theta star from below. And example or reduction, again, is to the same kind of binary, to the same little stone type tree. So in some sense, the instance that corresponds to the presence of the theta star is exactly the same difficult threshold example that we started with in the binary case. And it also serves even for the logarithmic loss and the logistic regression. Now, what is the hard case? Again, if you are already in the world of logarithmic loss, and the hard case seems somewhat strange, right? Because if this is my minimizer of the population loss, then why theta star can be unbounded, right? This happens where all points essentially belong to the same class, right? You just assign probability 1 to the correct +1 class, and of course your MLE doesn't, this classical example of MLE doesn't exist, and theta star goes to infinity, right? So if you are in the sequential setup, then you may relate this kind of construction into the same, the same little stone tree, the same decision of whether you're on one side or on another side with respect to a certain separator. And this is what makes it hard. At the same time, for the batch situation, if you are in statistical setup, this is the easiest possible setup. You observe only +1s, all your class +1s. You are quite certain, right? That it means that maybe with very high probability, the +1 is the only class that exists here, right? This again shows you the separation between sequential problem and the statistical problem. And here is, so we were jumping to the same setup. Like, what if we know x's in advance, right? What if they're known? And the nice result we can prove is that if you know x's, then there is an exponential weight-based sequential probability assignment. So it's like a way to assign classes sequentially to each new observation, such that the regret, like the sum of my log losses minus the loss of the opt, is upper bounded by up to some constant. Actually, the constant is very nice here, 11, right? Something like that. Is dimension log t. So there is no theta star anywhere. Little stone example is somehow bypassed inside, and theta star never appeared. And the case on the previous slide is never a difficulty. Like a little stone tree type construction never hurts. Now the question was, why do we assume x's to be known, right? Again, there are two aspects. One of them is more like a playground to test what's happening, but the second one is we care about the statistical. Some of us here are doing statistical learning or are interested in statistical questions. So what if we try to adapt this probability assignment and convert it into a purely statistical result, right? Like, what if I observe the IID data? And this is, I'll just jump maybe first with the algorithm, and then I'll just do the implication first. It appears that if we are in the statistical setup where I know all x's, so I observe the sequence of xi, yi's of length t, then I can convert the predictor, the one that is sequential for the setup when the x's are known in advance, into a statistical predictor such that its expected excess risk, there is no regret anymore, is d log t over t, right? Where t is the sample size. And again, the magic here is that there are no assumptions on the distribution of x's, no assumption on the distribution of y's. It's realizable or agnostic or whatever. X may have zero moments. It's not necessarily integrable. So there is nothing, and this follows directly from this sequential analysis. Of course, how do I define then this expectation? You might ask me, the idea is that if axis is not integrable, still when I'm taking the inf, 0 is one of the potential solutions, right? A 0 vector. So therefore, this is at least log 2 when you put 0 here for the sigmoid. So this always exists. And the predictors are exponential weights. They will mix up together so that this is also integrable, no matter what the assumptions on x and y are. So this is some magical measurability aspects about that. And the last thing, I think I'm almost out of time. I'll just tell you about how the algorithm works. So I mentioned that this is exponential weights based algorithm. It's a bit tricky because it combines the exponential weights, so the kind of the mixture of the sigmoids, with some kind of specific tricks that will allow me to bypass this unbounded theta stars, which will allow me to bypass the problem of very large norm of the optimal solution. So let's take a look at potential. I think it's gray again on these screens, and here it's almost the same color. So there are kind of, if theta star is some optimal solution for the minimizing of this logarithmic loss, then I can split the whole domain of points, or all my observations, into 3 zones. So there will be some areas, or these 2 areas, where the points are assigned either with one class, like essentially realizable, or with the other class. Just because if there is a point with, say, class red here, then it will mean that theta star has a misclassified point with a large margin, which is impossible because 0 is one of the potential optimizers, right? It will never put too far away points that are misclassified. Therefore, at some level, or at some width of the slab, all the points will be either +1s or -1s. And then there is a bounded slab, like it's not a ball, it's really the slab, like 2 half spaces essentially, right? Such that I have a mixture, like I can have both red class and blue class. And the whole idea will be to do the following: to find such a slab where I have representative of 2 classes. I call it the gray zone. And in this gray zone, we have a very specific exponential weights type algorithm whose prior uses the knowledge of all x's. So here I just kind of use the standard thing, and I think of the problem as bounded. While outside of the slab, I will assign probability 1 essentially because I know it should be +1. So I just put probability 1 to class +1 here, and I put probability -1 to the point here. And then because the slabs, they form a VC class, I can do a next level of some aggregation. So it's like exponential weight over exponential weights that will allow me to pay, actually, in terms of the regret bound, relatively like a modest price of aggregating or finding this slab. In some sense, the problem is split into the realizable and non-realizable parts. Realizable is resolved using knowledge of x's and assigning deterministic probabilities, while inside the bounded sets, the exponential weights with a particularly chosen prior works. Again, magically, this gives you no assumption on theta star in the final regret bound, only dimension and the number of rounds. Yeah, and I think I'm 1 minute or maybe almost there. I'll just mention that the same phenomena happens in the hinge loss. So we just tried it, and you can run the same kind of principles with the hinge loss. Hinge loss is somewhat slightly more complicated because you also have this margin parameter that appears here. And again, if you don't know x's, you run exponential weights, you mix everything carefully, and then the regret bound will depend on the norm of theta star and on some parameter eta, which will kind of put the dependence on margin under the logarithmic factor here. And again, if you twist or if you improve this a little bit, we know x's, we jump to this setup with no x's, then it's possible to completely remove the dependence on both theta star and eta, or like 1 over gamma under this logarithm, which will give me, for example, a result similar to VC style result, right? Like it's a bit in this direction where you don't pay anything for margin or anything for the normal of the solution. You just count the number of mistakes. Here you just count the total hinge loss. I think that's it. Yeah, if there are any questions, I'll be very glad to answer them.
You were assuming that you access to all the xi's, all the values. Is it a relevant question to ask that, oh, if you only have like good big enough set, but not all the t values?
You want to see a subset? Yeah, I think maybe in the statistical setup we have IID, it might be maybe enough. But I would say that in a worst case adversarial, I think the adversary will play with the fact that you haven't seen something, right?
Problems are where establish separations so that, the star, there's a low set.
Yeah, I think okay for definitely for 2 out of 3. So for logistic regression, yes, you have to pay theta star from below. Just again, the reduction is to the little stone example, and for hinge it's the same. So it's slightly more subtle with the squared loss. The squared loss, there are some exceptions. So it behaves slightly in a slightly different way, but these two are exactly related, or like are exactly reduced to the little stone tree.
The online to batch, is it like a standard online to batch, or is it also some transductive thing that you have to know the point at which you want to make a prediction to?
Yeah. So in some senses, it will be the same exchangeability argument, but it will be something like you give me a new point, and given a new point, I have a collection of x1, xz, my observations, and I have this as a test point, and I'm running my algorithm on this, and then there is like the same exchangeability argument works.
So maybe I missed this, but so towards the end, you talked about, okay, you can get the results from the transductive case to imply the bypassing the bound in the IID case, right?
Yeah, from transductive online, you immediately jump to statistical IID case, right?
And what about the smooth case?
Smooth case is just, I think it's somewhat slightly different. I think it's still for the online world. So I think people were also kind of annoyed by this little stone tree simple example. And then we're focused on the regret itself. Like the for binary loss for VC case, as I mentioned, the transductive, when you know x's, the problem is completely trivial. You just, if you know x's, project your VC class, the entire VC class on it, and then use halving. So there is essentially nothing to prove for the binary loss, but there is something interesting happening for other losses. That's essentially what this talk is about.
Talk about sparsity in the logistic case. I was thinking the higher that you talked about earlier.
Yeah, I think it's possible. It's just a matter of we didn't do this computation. So the sparsity here is more or less to show the proof this concept or this idea works. And we were not maybe trying to. There is a recent paper on hinge laws doing somewhat related also like the sparsity there, right? So I think there are some papers also around trying these ideas.
Any other questions?
Yeah. So for the logistic case, like what is the maybe you mentioned it, but like what is the computational complexity?
For which in particular? For this one.
Yeah.
So right now it's not perfect. It's exponential in dimension. So it's bad actually. yeah, it's polynomial in T, but it is exponential in dimension. Yeah, it will be very interesting to understand whether there is even a polynomial time algorithm that achieves this with no one access. Even in the IID case, even in the batch case, I think nothing is known. What is known actually is the polynomial time algorithm that achieves this with the norm theta star here. And this is essentially because you can reduce the sampling to some, again, it's sampling from log concave measure for exponential weights in the logistic case. And there are some polytime algorithms. So this is not necessarily super efficient, but you can do the polytime approximation. Now the problem happens, at least we don't know how to do it yet, is when like it's really restricted there. You really need kind of a ball of a certain radius for theta. So if you are unconstrained, then the analysis becomes more complicated, and we needed this geometric idea of essentially separating, right, between the points that are certainly classified, essentially realizable. And here, for this part, we can do the exponential weight, which is polytime. So this is like a polytime component. Then this is like very efficient, but then we need to aggregate up to exponential in dimension number of these slabs. And we have another additional result where we do some in the statistical setup where we make some assumptions on the density, some additional assumptions, and then we have a fully polytime algorithm there. But we really need some extras. So we don't know how to adapt to these thresholds in the computationally efficient way in the worst sequential case, because you have to really, so far, at least for analysis, you have to adapt for all possible locations of these separating slabs.
Okay, thanks again.
Yeah, thank you.
Okay,